So welcome everyone. Thank you for being here to the first ever joint EGU, AGU Early Career Geodesy webinar. My name is Stacy and I'm one of the early career reps of the EGU Geodesy section. And I'll be co-hosting this event with Orku, who is one of the EGU Early Career Geodesy reps. And this webinar will focus on the European geodesy landscape, exploring the diverse roles that geodesists play both inside and outside academia, as well as discuss different opportunities for early career people and strategies to hopefully attract more people to the field. So today we're extremely lucky to have three panelists. Professor Tim Wright from the University of Leeds in the UK, Professor Christian Seens from Delft University of Technology in the Netherlands, and Professor Manon Dalaison from Institut de Physique du Globe de Paris in France. So for the first half an hour, each panelist will talk about their career paths, their various experiences, and anything else they'd like to share with us about this topic. And then the second half will be a general discussion and Q&A. So don't hesitate to post your questions in the Q&A box and we'll get to it in the second half. All right, so I think we were going to start with Tim.
Great. Okay, so I thought I was trying to think about how to organize this presentation, and I know you wanted this for somewhat of a career perspective, so I thought I'd try and organize it around 3 satellite missions, all ESA missions that have been important for my research career. And the kind of timeline of those is, so those missions are ERS 1 and 2, which flew in the 1990s, MVSAT in the 2000s, and then Sentinel-1, which has been flying since 2014. And it kind of lines up quite nicely with my various career stages. And so what I'm going to do is kind of show you some highlights, some particular lots of interferograms that have been important and have been milestones in my career, and some perspective on what we're doing now in COMET and also in SatSense, using Sentinel-1 data in particular. I guess I want to emphasize the role of luck. I think in all of our careers, I've been really lucky on many levels. And I'll try and bring out some of those stories as I go along. Conscious I've only got 10 minutes as well. So ERS 1 and ERS 2 were flying when I was doing my PhD. And I guess a lot of people show the Landers interferogram, but the first piece of really big luck I had was when I was doing my master's degree in London in remote sensing. We had a presentation from Ren Capes, who worked at Nigel Press Associates, who were the first company to try and do INSAR commercially. And he came and he showed a version of this interferogram. This one's from a paper by Meyer et al. But it was the Grevena earthquake interferogram. And it completely blew my mind as a kind of geologist, geophysicist by training, that you could actually see the motion of earthquakes from space. For those of you unfamiliar with these kind of data sets, you can think of each of these interference fringes as something like a contour of the amount of ground movement, and the contour interval is about 3 centimeters. So the fact that you can see which bits subsided, which bits went up, which faults moved was mind-blowing. And I was also lucky because somebody on my MSc course, her dad actually worked in the Earth Sciences department in Oxford, and then she found out about this PhD on INSAR, which was the first one in the UK to work on INSAR for earthquakes. So I got to do a really exciting PhD project looking at earthquakes. So this was the first interferogram I made. It was 1 year into my PhD before I made my own interferogram. It took quite a long time. It wasn't a whole year of processing, you'll be pleased to know. But this was the Dinar earthquake in Turkey, very normal faulting earthquake that I worked on for my first paper. But my main PhD project was really about interseismic deformation. Could we actually measure the buildup of tectonic strain before earthquakes happen? And I guess it's also, you know, one of the low points of my PhD was we had a presentation, a seminar from Eric Fielding, who was then and still is an INSAR guru at JPL. He came to Oxford, gave a talk about INSAR, and someone asked him whether you can measure the buildup of tectonic strain before earthquakes with INSAR, whether he thought that would be possible. He said, no, that's probably impossible. And so that was about a year into my PhD as well, which was a low point, but we did it. And what the trick essentially was, in a single interferogram, the signal's too small, but you can stack those, or we did simple averaging. In this case, it was just 4 interferograms, looking at the North Anatolian fault, and this figure on the right shows those relative motions across the North Anatolian fault, consistent with the buildup of tectonic strain, moving about 2 centimeters per year in this case. So following my PhD, we had a little pause, and then there was ENVISAT was launched, and again, I guess a bit of serendipity. I was invited to do some processing for an event that happened in Ethiopia. There had been some small earthquakes, and working with my PhD student at the time, Juliet Biggs, now professor in Bristol, we produced this interferogram in Afar in Ethiopia, and actually, again, an astonishing amount of deformation, more fringes than we'd seen in any other interferogram we processed, way bigger than you'd expect for the earthquakes. There was a small, relatively small eruption. There's some people for scale here, but really what was happening here, there was a large dike intrusion. And I guess it's another sort of career life lesson, really, and that this was clearly a really important event. And I ended up spending probably most of the next 10 years working and thinking about Afar and working on this region. So I want to move on to Sentinel, as that's been obviously the focus of more of our recent work. The first interferogram that we made for Sentinel was quite early, not long after launch. There was an earthquake in California, in South Napa. It was a relatively modest earthquake. A strike slip earthquake caused this rather lovely deformation pattern here. I think that the thing that was really amazing about Sentinel right from the beginning was that we were getting quite short revisit times. So with Sentinel-1, we had images every 12 days with a single satellite with 1A. And so we were able to get this image for the 12 days following the earthquake that showed rather beautifully this post-seismic creep. So we're starting to see processes on timescales that we weren't able to see before. And Sentinel-1 really has been a game changer for what we do. I think 2 main reasons, possibly 3. First of all, it's a kind of boring mission in a way. It acquires the same data in the same places every time, so you don't have to think about all these different modes. So if you look at other satellites, they can be in different beam modes, different polarizations. Sentinel-1, you don't need to worry about that. It acquires data pretty much over the entire globe, certainly over all the tectonic and volcanic areas. So when there's an event, you know there's going to be some data, usually within a few days. The other, I think, really important thing is that the data is completely free and open, and anyone can use it, whether that's for academic purposes or indeed for commercial applications. And that means we could think about processing data at scale. And that's what we've been doing in COMET, which is an organization I run in the UK. We've been processing Sentinel-1 data over all the global volcanoes and some of the tectonic belts, really focusing on the Alpine Himalayan belt. And we're nearly at 2 million interferograms now, and those are all available for anyone to download and use for whatever purposes they want. Our main purpose in COMET has been, one of them has been to map the tectonic strain. Is our latest result from Tibet, showing the east-west velocities. This is from tens of thousands of interferograms combined to give us these long-term velocities. So it's really building on that work way back in the PhD, but now we're getting much more precise data. We can see these beautiful changes in color here associated with relative motions across individual fault structures. On a much smaller scale, another thing working with my colleague Andy Hooper, we realized that Sentinel-1 offered an opportunity to really kind of shake up the way that commercial INSAR was done and actually provide a lot more data more cost effectively to people who are interested in hazardous ground movement. One of those organizations in the UK is the Rail Authority. This is a 3D view of Folkestone. This is the railway line here running along the bottom of the cliff. And this is a long, very large landslide. You can see these red dots associated with subsidence, blue dots associated with uplift at the toe of the landslide. And you get those velocities, but you also get the time series, and you can see that motion isn't steady in time. And we're interested in these kind of big structures that are impacting infrastructure, but you can also work down to individual houses. And the way we work in SatSense is we can process whole countries, keep those data up to date. We don't need to be selling the whole country, but we can sell you information about your individual house much more cost effectively. And we're really trying to make that data available for people who aren't experts in the data. So just to kind of wrap up, I think, and I've talked about, this is a timeline from an Easter diagram that they update periodically, but I've talked about these satellites, which have been really important in my career so far. There's upcoming missions, I think, that are also important. Sentinel-1D will be launched maybe this year, maybe next year. And then a few other missions are planned. We've got Roselle-A and Roselle-B towards the end of the 2020s. There'll be L-band SAR missions that will be in the same orbital geometry as Sentinel-1. There's also going to be Harmony, which are companion missions to Sentinel. They'll probably fly around Sentinel-1D, and they'll acquire different geometries, and we'll be able to get north-south motion, we'll be able to get up-to-date DMs from Harmony. So there's lots of really exciting things going on there. And even the next generation of Sentinels are being planned already. So Sentinel-1 next generation will be launched in the 2030s. So there's this pipeline constantly from ESA of these incredible satellites that are enabling really important science. And I should mention also Earth Explorer 12. I'm involved in a mission advisory group for a candidate mission called HydroTerra, which would be a geosynchronous SAR that would be able to stare, for example, at a volcano and perhaps give us hourly interferograms for that volcano. So it'd be a really incredibly powerful data set. And I should say also, I guess throughout my entire career, NASA have been trying to launch a SAR mission as well. And hopefully it's going to launch this year, assuming it survives your new president. So I'm just going to end by saying I have another real source of luck is the amazing people I've been working with, and a lot of the work that I've shown today is done through these incredible collaborators. So I shall end there and pass over to the next speaker. So thank you very much.
Yeah, thank you so much for sharing, Tim. So we can move on to Christian.
Okay, so my name is Christian Siemes, geodesist by education. I studied in Bonn. You see here a nice ChatGPT impression of a geodesist, and during my studies I learned how to operate that instrument so well that I can still put it up today, even though it's been 20 years past. Then during my PhD time, I stayed at the University of Bonn, but I moved into space geodesy. And particularly, I was working on the GOES mission and deriving gravity field models from GOES data. And back in the day, that was actually a quite substantial problem because you get hundreds of millions of observations, all correlated. And you had to estimate about 100,000 parameters from these observations. And that could only be done with supercomputing. So at that time, I was also exploring the possibilities of supercomputing. And here you see one of those supercomputers in the halls in Jülich Research Center. Unfortunately, I couldn't really find the picture of the supercomputer we were using back then. But it's still the same building. After my PhD, I moved to, for the first time, to TU Delft. I had to switch mission, so I was moving from the GOES mission to the GRACE mission, also switching from the static or mean gravity field to the time variable gravity field. And one of the goals there was to estimate more realistic or more accurate trends from the time variable gravity field. So that was like a postdoc for a year and a half. And then I was lucky enough that I found a research fellowship at the European Space Agency. And this time I had to make an adjustment from gravity field modeling to instrument data processing. So I actually went back to the GOES mission, but then I had to take care of the data processing from the gradiometer in particular, and also attitude sensors. And all that happened at ESTEC in Noordwijk in the Netherlands, so not really far from Delft. And then I was, Tim said it nicely, sometimes you are lucky when the dice are rolled. So the GOES mission ended on 11 November 2013, and the SWARM mission was launched on 22nd November 2013. The mission manager of both missions was the same person as for the mission scientist. And it also happened that the SWARM mission had an accelerometer on board, and they were desperate to find somebody who knew about accelerometers. So they decided, therefore, to keep me at ESTEC, although not as a research fellow anymore, but I was converted to a contractor. And well, you can see it here. The contracting company was RIA Groups. But except for that, nothing really changed. So I was still sitting with the same computer in the same office with the same group of people around me. But I was now focusing on the SWARM mission. And what also was an interesting change was that while for gravity field purposes, you have an accelerometer to get rid of non-gravitational accelerations. But for the SWARM missions, it wasn't to get rid of them. It was basically the signal that you wanted to extract to derive air drag and study the coupling between the neutral and the charged atmosphere. So that was a quite different perspective on the same kind of data. And then I served for almost 10 years at ESA, so basically also outside of academia. And then I decided to, when I got the chance to move back to academia in 2019, I still focused on non-gravitational forces, but this time not so much related to the instrument data, but this time more on the observational level. And the primary observation was air drag to derive thermospheric density. So there was already quite a long cooperation between me on SWARM and the scientists at TU Delft who were doing that. And then the key person decided to move to another institution, and I was able to fill that gap. But since I had already quite a lot of heritage in instrument data processing and also attitude reconstruction from star cameras and other attitude sensors, I'm part of my project work is now also focusing on the development of the next generation gravity mission, where my contributions will focus on the attitude reconstruction, the accelerometer data calibration, and also anything related to accelerometer data processing. So this is how I got to Delft. I have a position as an assistant professor, and yeah, I mean, what seemed like a long academic journey in terms of kilometers on the map wasn't actually so much. So I was basically born in a small town near the Dutch border. Then it's just 100 kilometers or so to the University of Bonn. And then you make a move like 300 kilometers to Delft. And then you have like 35 kilometers between Noordwijk and Delft. That was it about me. Thanks.
Hello, everyone. So thank you for attending the webinar, and thank you to Stacy and OQ for the invitation. So I'll go through a single slide presentation to stay in the allotted time. And so to introduce myself briefly, I'm Manon. I work as an assistant professor at IPGP in Paris. So I started this job in September 2023 So I'll contribute to the discussion on the geodesy from my perspective as an early career researcher in France. So how did I end up as a researcher at IPGP? I started with a Bachelor of Science degree at the Australian National University, where I learned many things about the Earth system science and how research works. And it's towards the first year of my bachelor that I first heard about geodesy as a scientific field through a class that was talking about GNSS and gravity, so more the applied side of geodesy. Then I pursued my studies with a master degree in France in geophysics, and then I continued with a PhD in Paris, followed by 2 years of postdoc position at the French Alternative Energies and Atomic Energy Commission. So this is how I became a researcher at IPGP in a geodesy team with many colleagues working in different fields of geodesy. And so at work, my time is divided between research and teaching. I have about 200 hours of teaching per year. And in my research time, actually, a lot of time is dedicated to discussion with colleagues and students to work in common projects and supervise interns. So there are two main axes in my research. I work on the INSAR processing, so the technical part that Tim already introduced. So you see from the colorful background of this presentation that this is the kind of image you can get with INSAR, so interferometric synthetic aperture radar. So you work from satellite images to get ground deformation. And so this transition from the images to the ground deformation and tracking this deformation over time requires some optimization about the computing time, the different processing steps that can be improved to get more accurate deformation and also to track the uncertainties. So I believe that this technical work on INSAR is something that I relate to geodesy. So how can we improve the quality of the signal and work on what's inside the data? On the application side, I work with, I'm interested in quantifying the deformation, the surface deformation around active faults and above aquifer systems, and how we can learn things about the subsurface and the processes that occur underground from the surface deformation we have, and the associated sources of error, which are the atmosphere, the vegetation, and other processes. So now to go back to a more general perspective about geodesy, I thought that to talk about the future of geodesy and also the different opportunities that are now available, it's good to distinguish between the global geodesy, which cares about the orbits, reference frames, and the global gravity field, the geoids, and keywords like this. And also the more applied side, which is clearly complementary, and both field of geodesy have to work together to estimate a precise ground deformation and also map gravity, and this over time because of the time component, the changing component of all those information is very important. And this vision of geodesy, of course, is useful for science, for it's a requirement for many observations, mostly satellite-based, but also ground-based, and also society in general that motivated the development of geodesy also. So related to military applications, but also for Tim showed the railway project, so about infrastructures and the stability of the ground, and also working with in the context. So on the right you have some key ideas. Also the current context is we're in a world that has climate change. To quantify sea level rise or ice melting, geodesy is a key technique. There is also all the questions about natural hazards, so earthquake related or volcanic eruptions, and also climate hazards. So, and also resource monitoring is key. And I think Geodesy can help a lot with resource monitoring. And on my side, I care more about water. So how do we track groundwater variations, and how can we estimate the storage capacity of aquifers? Also, I think now, so you saw the example of the LEAKS platform from Comet. There are a lot of other European initiatives in availability of SAR data at different levels. So you have raw projects, and you have directly deformation projects that are available. So an example is the EGMS Copernicus platform, so European Ground Motion Service. That is freely accessible and easy to use. And there are also French initiatives related to Formater, and ESDeform is a French initiative observation that is currently under progress. And so they're trying to make a map of ground deformation for France and the French territories. So that's all on my side. Thank you.
All right, thank you so much, Manon. So now we're going to move on to the more general discussion and Q&A part of the session. So Oiku, do you want to lead that part?
Yeah. Well, thank you everyone for sharing your journeys in your journey in geodesy, and it was actually refreshing to see like different countries and how things progress basically. So we can start with the discussion. Meanwhile, our audiences can write up. We can start with some questions that we came up with. So one thing that we are curious to hear actually is the current state of geodesy where you are. Can you give us a little bit more insight? Like, what is the current state of geodesy in the country you work? How do you see it evolving in the future?
Shall I start? I guess I know most about the particular kind of geodesy that I do, so the deformation studies. I think there is a healthy university sector, so there's a lot of research going on using geodesy from INSAR, from GNSS for different applications. I think we within Comet there's a lot of opportunities there. So for PhD students, for early career researchers who might be interested in postdoctoral positions, or to join us on fellowships, there's lots, or internships. We have lots of opportunities there if people are interested in using geodesy for earthquakes and volcanoes. I think one of the things that has changed maybe in the last 5 or 10 years is that there has been this sort of growing commercial sector in using INSAR in particular. So it's not just SatSense, but there's a number of other companies in the UK that employ some of our graduates from Comet. So there's there are opportunities there for actually applying these techniques to real world problems, whether it's the railway lines or dams that are collapsing, or some of the other examples I've talked about, individual homeowners. We work with in the UK. There's a lot of deformation from the legacy of coal mining, so there's a lot of ground movement still from old coal mines that needs to be monitored. So there's a whole range of different applications where the geodesy is really providing information in the real world. So I think there's lots of opportunities there. It's obviously still a relatively small field. I think we probably overall there is some fundamental geodetic research done in the UK as well, but I think maybe in some of the more gravity in other areas, perhaps more of that is done in other places, and that might be an opportunity to hand over to Christian.
From my perspective, I think there's very many examples of geodesists now penetrating other fields of research, particularly space situational awareness. And the general situation is that more and more large constellations are being deployed into low Earth orbit. And most famous one is obviously Starlink. And we will get to a point where satellite operations are really impacted by that. And we're not talking yet about crashes or anything. We're just talking about the situation where you get a warning of a potential collision, and then you must decide whether or not to become active. And at least for big agencies like the European Space Agency, that's becoming a problem because they get more and more alerts, and then you get to activate a whole team of really well-paid people, which costs a lot. So there's something a problem evolving, but there's also data appearing to solve that problem, because many of these satellites nowadays have also GNSS receivers on board. And that means that we can actually move away from the classical radar tracking of space objects to help understand atmospheric drag to a much more accurate data source, which would be GNSS tracking. And that's where geodesists come into play, and more accurate data becomes available. So that's current development that I see ongoing, where I think that geodesy can play in a very important role by infiltrating basically a completely different field of research.
Yes, maybe I can add also on the satellite tracking system. There is a DORIS system also that is French, and I have colleagues working on this. So that's also a field of research. On the French side, geodesy is often, I think it's very active, but it's not necessarily called geodesy per se. There aren't that many teams that say they're geodesists. Maybe it's also because of the definition and this idea that the geodesists are very theoretical physicists, mathematicians. So there's this vision. And so, but there is clearly a lot of work, notably linked with applications and working with new data. We have new instruments. The SWOT mission, I think, with the altimetry on land and the water surface mapping is something that will give a lot of work to with many potential applications. There is also the question of looking at coastal zones, also again working on natural disasters. And in France, an active source of funding for geodesy is a French Spatial Agency, CNES, that is funding a lot of research projects that involve geodesy.
Yeah, I mean, also from all of your presentations, it was kind of obvious that like geodesy is very much intersectional, let's say. You have to get into other disciplines if you want to continue. Also, in a recent Nature article, it was saying that 40% of the postdoctoral researchers are leaving academia. The ones that are staying are the ones who decide to change their topics after the PhD. So dive into a different field and use their expertise in that. I'm kind of curious, like what opportunities are available for early career geodesists in academia and government and industry. I mean, you kind of mentioned this, but maybe if you were to give an advice, what would it be?
That's a hard question. There are opportunities, I think, there. I don't know. I think my career, it's been you get to a point and you're presented with some choices, and then you make a choice, and then you don't worry about it, right? You go for it. But I think so. I sort of ended up on this path that was not a planned routes. I certainly, when I did my master's degree, I didn't want to do a PhD. I thought I'd go and get a job in the satellite industry. That was my thinking at that point, and then I got really excited about INSAR, and that kind of changed what I do. So I think if you do know what you want to do, I guess it's a different tactic probably, rather than just hoping something will fall on your plate. I get contacted a lot by people asking for opportunities, and we have sometimes we have funded positions within the Comet Group and other postdocs. So if you're finishing a PhD and you're looking for a postdoc position, do check out the various social media feeds, the UNAVCO mailing list, the various Geodesy mailing list, LinkedIn, all these kind of places that we don't look on Twitter anymore, but other places. And there are potentially things where we're advertising, so do apply to that, but get in touch. We don't mind people getting in touch. There are then also opportunities where people can apply for their own funding. So there's a scheme in the UK called the Newton International Fellowships, where you can put a proposal in, get some funding. We are now back in the European funding system, at least, even if we're not back in the EU. So people can apply for European Marie Curie fellowships if they want to come to the UK. So there's a number of opportunities there where that people are eligible for if they're interested in that kind of academic route. So get in touch. We can. I might not be always the fastest at responding, so don't. But I usually respond eventually. But also look on the Comet website, and there are lots of other people within Comet you could contact as well. So yeah.
Maybe just a follow-up question. Do you know, like within the UK, are there more like government-oriented jobs in geodesy, like maybe equivalent to in the US, the National Geodetic Survey?
Yeah, we don't have a National Geodetic Survey. I guess we have some geodesists. Well, there's the Ordnance Survey, which will do some geodesy, and I don't know much about what exactly they do. They run, I think, a national network of continuous GPS, for example. So I think they're probably quite a small team there, but I don't know much about that. There's also the British Geological Survey as well. So that's another route where there are some geodesists within the British Geological Survey as well. So there's definitely some opportunities. Also, I think within the ice, the cryosphere community, that there's the Antarctic Survey will employ some people with geodesic skills as well. So there's a range of different applications. I think my sense is a lot of the academic work is application focused, and then there will be some opportunities in particular sectors. But, yeah.
Okay. Great, thank you.
Is there anyone else who wants to add something?
I think the most important thing is that you do what you love, because only then you will excel. And whether that leads to a path in academia, where probably you have to be at the right place at the right time, or if you just decide to follow a non-academic path. There's also opportunities outside of academia where you still do a lot of research and development, which is almost the same activity as doing science. I think that the main difference is that if you end up in academia, you go to scientific conferences and present your findings, whereas if you follow up on a more industrial path, then you go to industrial congresses showing your new fancy instruments or new fancy products. But the process behind it is still probably very much similar.
Yeah, I guess this is to respond to both what you said. It's kind of difficult to do that switch. I believe, to say I've been working on this for a couple of years and then try to explain how this is useful to a different field or to industry. It is quite tricky. I guess this kind of connects to the question that we got from the audience. How is the field is brought to general public attention to get people to the academia path, it need to be promoted at some point. I guess they are talking about how you can do how you can explain what geodesy is to general public.
Yeah, I think this is a very important issue in France. Is really geodesy is an obscure thing that you don't learn about before the master level. And I think one of the biggest promoter of geodesy in France is a national survey, the national information, geographic information. It's called EGN, and it's where the team that is working on the International Terrestrial Reference Frame, they're a researcher in this institute. So this is kind of the only place where they speak a lot about geodesy. But you also have all the GIS applied fields in the industry, and like there are many opportunities also in these directions, and it can be linked with research as well.
Yeah, I guess I'd only add that probably people, geodesy is quite technical, and some of the details may not be interesting to some of them public. Obviously we're a biased audience here. We're all fascinated by the technology, but I think people are interested in what you can do with it, right? So if you go and talk about the fact that you can see volcanoes swelling before they erupt, there's a lot. It's very straightforward to give public talks about this kind of work. So there are lots of and I'm often going to actually the geophysics. It's geodesy fits within the Royal Astronomical Society in the UK, and there are lots of astronomy groups that I end up going and speaking to. We try and go out to schools, and so there's lots. We try and do our best, go to science fairs and things like that. But it is, it's a full-time job. Something we've just actually employed somebody in Comet to focus on kind of the outreach and work, and to try and do that. But I guess we found that going in via the sort of earthquakes and volcanoes route is easier for the particular type of geodesy that we do, because people get excited about those. But so that may not help with a broader shortage of kind of technical geodesists, I guess.
I also still remember at the end of my studies, we always had a problem in Bonn that there were not so many students. And that was when the university, or basically the geodesy, decided to go to school fairs where they get kind of a overview of what kind of studies exist. It's a little bit like a mini congress for pupils where they can just shop around and see what kind of things they do in different kind of studies. And once they started doing that, this kind of outreach, then you could really see that the number of students increase in geodesy in Bonn. So that was, in my time, it was like 30, 40 students who started, and I think at the peak they had 120. So that was a nice change to observe.
That sounds great. I mean, it's always good to see an increase. I know that in some universities they had to close down the geodesy section, or geomatics as it passes. We have some questions. It's great. So maybe we can start with how can European universities contribute to bridging the gap? Because there is a growing global demand for geodesists, but how can you do this by enhancing education and training programs in the field? Are there any current European initiatives to foster a relationship between academia and industry to support young professionals? If there is one that, maybe you can.
Yeah, I'm not sure. I think one thing that comes to mind, I guess, is the European Space Agency training programs that they have periodically. Again, I'm obviously thinking from my perspective that there'll be a radar remote sensing training course. I know we're talking to them at the moment about trying to plan a training course in sort of using Earth observation geodesy for natural hazards. So that would be, I think, fairly open in terms of its audience, probably mainly pitched at PhD student level. I don't know about other initiatives, maybe Christian or Manon have other thoughts about what could be done on a European level.
I mean, here in the Netherlands, we anyhow, I would actually not know at which university in the Netherlands you could actually still study geodesy. In Germany, in my home country, there are several possibilities. But here, don't remember where you could do it. In Delft, not anymore.
Yeah, I think we have general sort of geomatics kind of surveying type courses, but probably not a geodesy course in the style of a German geodesy program. Even keeping up broader programs like geophysics has been challenging over the last few years as kind of student numbers, it's been a struggle for student numbers, and university funding in the UK is challenging at the moment.
Yeah. I guess it is partly related to the funding situation, and like the departments are closing down, and it's a bit tricky. I can see that it's a common question in the Q&A box that there's the mention of the dramatic drop in the number of geodesy programs, and for instance in Newcastle. Students move to other topics like computer science because that's more there are some programs that are more attractive to young youth, and it's, I guess, common. What can we do? What are the strategies to attract more people to the field, and how can we manage to prove the point that geodesy is very much needed currently?
Yeah, I think it's also the problem we see in France, the number of students, not necessarily the funding, but students are not or are less attracted to do this kind of things. Also, mainly because they don't know about geodesy, or they don't really know what we do. So yeah, going to high schools or to the first year of university, going to talk with students, I think is a good effort to attract people. And yeah, talk about volcanoes, earthquake, as said Tim, but also water, climate change, sea level rise, ice melting. This is all related to geodesy, but it's not. It's a question of vocabulary, and also being attracted to the more mathematical side. But many engineering type students in France, engineer studies are quite popular, and I think they could be attracted to what we do. But it's something to think on the long term. It's
yeah, completely agree. I mean, we have it's really not strategic at all in the UK what degrees are done. You know, each university is competing with every other university for students. You know, we know that there's a shortage on the government shortage occupation list. There's certainly geophysics, and I think geodesy is on there. Those kind of roles where those skills are needed are on those lists. You know, we're often hiring people from outside the UK. The window cleaner is outside, so apologies if you can hear that noise. But we have to we're competing on the student level. If students don't want to do a degree, it doesn't matter if there's a shortage occupation. So you've got to make those options attractive. And I do think that climate change, a lot of school students are really motivated by the kind of climate change and those kind of hazards, climate change, those kind of issues. And actually, if you can sell geodesy as the tool we need, you're good at maths. Use your maths and physics to help save the planet. I mean, that's essentially the kind of motto we've been trying to use for our geophysics programs, where there's some geodesy on.
I really loved was at these student fairs, they have like, when they do the advertisement in Germany, they sometimes bring this block of ice, a really big block of ice, put a few minifigures on it, And then they write down the number of these blocks of ice per second that Greenland loses and how you can measure them with gravity missions and so on. That usually catches quite a lot of interest from interested little pupils.
Yeah, on the level, I guess we need to change a little bit how we advertise it. We need to be also interdisciplinary. We need to understand the interdisciplinary nature of geodesy while we are also advertising it. I will leave the floor to Stacey. She will continue with the next question, maybe.
Yeah, we have new questions coming in. A good one, well, they're all good questions, but what is the impact of AI on geodesy? Will AI and geodesy integration open up new avenues and opportunities in the future? Do you have any thoughts about that?
Who wants to start? Christian.
I mean, from my perspective, it just gives us slowly but surely a headache in education because we need to modify how we ask or what kind of projects we give to students. It's clear that we can't avoid AI, so we have to consider it as a tool to use, and we need to learn how to use it still. But I think to see how that impacts a specific field of research, it's still a bit too early to say exactly. But of course, I mean, formulating texts, getting a small piece of code to work, structuring information, all these kind of things, that's where AI slowly starts trickling in until you see the bigger picture emerge, how AI will shape a field.
Yeah, I agree. I think at the moment it affects more the way I teach than the way I do my research because I feel the conventional robots, they're not or like they don't understand what I do as a research. So, but for writing it helps, and it's also a perspective, a tool for massive data because now we have more satellites, we have more incoming data with all kind of errors or all kind of patterns. So machine learning is good at identifying the patterns, and I think this will be clearly a way to mine into the data and extract interesting signal.
Yeah, I think from our side, we're already so colleagues in, well, so my colleague Andy Hooper in Leeds and Juliet Biggs and colleagues in Bristol have already sort of been testing AI tools using the INSAR data. So one of the things we have operational on the COMET website, you can click on individual volcanoes and you get an AI flag. Has it seen some fringes in the interferograms that look like then they are volcanic deformation? So that works pretty well, actually. There's a couple of papers on that you can go to on the website. So otherwise, you're manually looking at thousands of interferograms, continually, and you would never spot everything. So it's a way of sort of flagging those signals. So I think that's works pretty well. I think the work that Andy, I guess another area that there's been a couple of PhD students working on thinking about phase unwrapping, which is a real problem with INSAR, and actually there's some promising work being done using deep learning to solve the phase unwrapping problem, which will be great if I think it's sort of on the brink of being better than other unwrapping tools. Andy is thinking about using it for sort of prediction or forecasting. I should use more conservatively. If you're monitoring volcanoes, can you use the kind of deep learning video prediction type algorithms to say what's going to happen next at an individual volcano, not just based on what's happened at that volcano, but what's based on your knowledge of what's happened at all other volcanoes. So I think there's some interesting avenues of research, and will definitely grow as we go.
Great. So I'm just going to ask one more question, then we'll have to wrap up. So one of the question is which of the geodesy application you envision to be the one with more demand in academia now and in the near future? So might have a slightly biased crowd here with the the INSAR. So in my perspective, I think the future is combining a lot of these different technologies. So INSAR, GNSS, GRACE, SWAT, and see what we can learn with the combinations of these different techniques. Do you have any thoughts about this? Yeah, like which technology should early career focus on? Yeah.
I think I would say focus on the problems you're trying to solve and not the techniques. So, you know, are you interested in water resources, volcanoes, you know, the changes in the mantle, or, you know, GIA, you know, what are the problems you're trying to solve, and then learn the tools you need to solve those problems. That's been my perspective on
I agree.
I would say if you're a student and you want to stay in academia, then it's usually a good thing to watch out for upcoming satellite missions, because usually once it's launched, there's always somewhere a bigger research project where they start hiring several PhDs or maybe even postdocs. So I guess, for instance, in Germany, Gravity with the upcoming NGGM mission, that might be a good bet.
Yeah, nothing much to add. I would say we didn't talk a lot about the sea bottom, but I think this is an area also that we will have lots of future research, because most of the Earth is covered by water. So what do we do on those regions? And yeah, upcoming missions, and also working on the link between what we have on the sea and what we have inland. So the coastal zones also is a area that we need to understand more.
All right, so we're right at 8 a.m. So we'll wrap it up here. So I just want to thank one more time our fantastic panelists for telling us about their career paths and hearing more about opportunities in the different countries. And thank you so much, everyone, for coming.
Yeah, thank you, everyone. Thank you to our speakers. Thank you to Matt and Stacey for making this joint webinar happen.
And I'll just add one final comment, which is we hope to continue these. So if people have ideas, you know, Stacey and Oikuk came to me and suggested this one. I think it's a great idea, but let's keep these going. If people have ideas of speakers or topics, please let them going, and hopefully we'll do more of these AGU, EGU webinars.
Yeah.
Thank you.
Thank
Thank
you.
you. Bye.
Have a nice day. Bye.